My name is Juan Toscano. I'll be your host today. Today we have one speaker. She's Taniya Kapoor. She's a PhD researcher at the TU Delft. She specializes in scientific machine learning applied to engineering structures, and particularly in the railway engineering. She works under the mentorship of Doctors Hongri Wan, Alfredo Nunez, and Professor Rolf Dubler and Daniel Tardab. Tartakovsky. I'm sorry if I mispronounced your name. Before her PhD, Taniya was an intern in the GAM lab in ETH Zurich, focusing on physics-informed neural networks under Professor Siddhartha Mishra. She holds a master's degree in applied mathematics from South Asian University and the University of Delhi, supported by notable scholarships. Her bachelor's degree is in mathematics from the University of Delhi. Her research aims to fuse scientific machine learning with engineering practices. Taniya, please, with this short introduction, please start your talk.
Many thanks for the nice introduction and thanks for the invite. So this is Taniya. I would like to present our recent work on neural oscillators for generalization of physics-informed machine learning. This is joint work with TU Eindhoven and Stanford University. So first, I would give you the overview of my presentation. So my slides are divided into 5 parts. In the first part, it's the introduction part. Here, I will discuss about the overview of my research overview, and the current strategy which have been utilized of so many years in railway engineering structures, which are based on data-driven strategy. And the challenges on those strategy I will discuss. And then my work, my PhD is based on utilizing the physical knowledge which have been here like so many years. So with that, in the second part, because my work is to utilize those physical equations which are in the form of mathematical equation. So in the second part, I will discuss about physics-informed machine learning. Here, I will give you brief description about physics-informed neural networks for forward and inverse problems. And also I will present like my previous research results, which is the foundation for the current work, which I'm going to present, which is based on generalization. So in generalization, basically we utilize neural OD methods. So in the methodology section, I will present neural OD methods, specifically 2. One is co-RNN, coupled recurrent neural network, and second is long expressive memory. And then because we propose framework, so I will discuss about the framework which we propose for extrapolation. And the fourth part of my presentation, which is results, here I will discuss about, I will present the results on most commonly used PDs on extrapolation. And the final part of my presentation is conclusion. Here, I will give you the takeaway and the contribution of this work, and finally, the future work which we are currently working on. So starting from the introduction. So here in the right, this is research overview, sorry. So in the right, as you can see, is the Netherlands map, and it's the railway tracks. These network, as you can see, is the railway tracks connected, very busy, as you can see, and the boxes are showing the trains, and it's like the normal day in the Dutch railway infrastructure, and it's highly occupied. It means that any problem here will affect entirely the network. So it affects various services and a lot of people. A busy railway network can become a continuously monitored network. So we need to monitor where, like, how much deformations are on the tracks is going, and how much the load tracks can bear. So it means that prior simulation at backend is essential before deployment. So my work is to advance state of simulation in railway infrastructure. With this, I would like to discuss about the current state of, So I would like to discuss about the current data-driven strategy which have been used. So when the train moves, there is the deformation occur on the tracks, and this deformation, if not maintained at time, then this will happen. we never noticed like we usually walk. So the database predictions, for database prediction, we have this train. It means we need to collect data. There's a CTO train. In this, like on board, several sensors are installed, and wherever the train passed, data is collected. And this train is not only utilized using only TU Delft is using for data collection. Also, the companies at TU in Netherlands are also using, like ProRail, also used for data collection. So all these, like the previous method for understanding the deformation, what is the right movement to perform maintenance, are based on statistical and data-driven machine learning. We do have lab prototypes in our labs. And also software simulation using ANSYS is also possible. But there are challenges using these strategies. What are the challenges? Database strategy actually requires lots of data, as the railway networks is spread thousands of kilometers. For instance, like in Netherlands, railway tracks are 7,000, approximately 7,000 kilometer large, and it's very difficult to measure the data at every location. But each location is equally important. For each meter, if we need to install a sensor, it means that we need 7 million around sensors. So it's difficult to install, and feasible number of sensor requirements. So it's challenging. Now, based on the lab-based prototypes, the labs we do have, but in the labs, it's actually not exposed to environment. And it's also, we cannot run 100-kilometer speed trains on the tracks which we have in our lab. So it's also confined in speed limits. In terms of, if I talk about simulation software, it also like integrate meshing, remeshing, even for the slide changes, we need to perform again meshing. So it's a computational costly task for collecting the data. So my work is to mitigate these challenges, and the theory, which physical knowledge, which we have over the years in our libraries to take the leverage of this physical knowledge. And these physical knowledge are in model in the form of partial differential equation, ordinary differential equations. So can we reduce data requirements or eliminate it? This is my PhD is about. So now I would like to move to the second part of my presentation, which is physics-informed machine learning. Here, there are the two scenarios, two possible scenarios. Like in physics-informed data-augmented learning, we have deep learning models, which leverage the physical knowledge, as well as some observational data, like sparse observational data. At certain location, we have some data and physical knowledge, and we want to build up a deep learning model. So this is like some physics, some data. And the second scenario is the purely physics-informed machine learning. Here, we are not interested to leverage sparse observational data. We have physical knowledge, but that physical knowledge must be well posed. It is not like ill posed, and we need some amount of observational data at certain location. So this is the idea about physics-informed machine learning. Now I would like to give you like the brief description about physics-informed neural network, or everyone knows. So I will be quick in this part. So here is the F is the operator, U is the quantity of interest, and small f of x is a source term. Here is the boundary condition and the initial condition. So here the most important requirement is the well-posed PD, and we are interested to get the quantity of interest. In the loss function of Pence, we have three terms: loss function with initial condition, boundary condition, and the residual term. So we need to minimize this loss function and train our neural network and get the best weights and bias and get the prediction, which we want quantity of interest. So this is all about the forward problem. Now moving towards the inverse problem. In inverse problem, our physical equation is ill-posed. It means some unknown quantities we do have. Either it is some parameters in the equation is missing, or initial or the boundary conditions are unknown. And since our problem is ill-posed, it means we need to provide some additional data at certain location, or some additional data we need to provide. And it's not the case like in inverse problem, we only have one unknown or two unknowns. We can have multiple unknowns, parameters in the function. So, but there is only one single change in the loss function. We have an additional term, which is the minimizing the data. This is the minor difference between forward and inverse problem. And we get the prediction of the quantity of interest as well as the unknown parameters or unknown function which we have in the physical equation. So now in the railway dynamics, two most crucial part is train track interaction, and this wheel is moving on the track, and catenary pantograph interaction. And these two scenarios can be modeled with beams under varying condition. And this moving load dynamics correspond to Dirac delta function, and our interest is to predict deflection and cross-sectional rotation of the beam. So how we can utilize the physics-informed neural network for the prediction of deflection and rotation? We need mathematical models. So we have three different scenarios. Like first is the Euler-Bernoulli beam equation. Here the force is applied, then there is some deformation occur. This is they do have theories like in Euler-Bernoulli beam we have deflection only. In Timoshenko beam theory, there is a little rotation when the force is applied. There's a rotation also considered. So we have two unknowns, which is rotation and deflection. Now, in the third scenario, which is system of beam connected by Winkler foundation, this is based on the Euler-Bernoulli beam theory, because here we only have deflection. If this model, we model using Timoshenko beam theory, then we do have four partial differential equation. Then we do have four unknowns like deflection for the first beam, rotation for the first beam, for the second beam also deflection and rotation. But we are considering this using the Euler-Bernoulli beam theory, so we have these unknowns, only deflections for both the beam. Now we are interested to utilize physics-informed neural network for simulating beam deflection. But there was challenge. What was the challenge? The challenge is that because this is made with aluminum has the multi-scale real material coefficient in the pin loss function. So the framework which we introduced, we first consider the dimensional multi-scale PD, and then we perform dimensional analysis and convert the dimensional multi-scale PD into non-dimensional uniscale PD. And then we utilize pin and we get the prediction, and finally convert the prediction into again dimensional solution. So this is the lossless transmission, because we didn't use like autoencoder to go in the some ansatz in latent space. So this is because we perform dimensionalized analysis, so we get the lossless transmission. There is like some plots from the paper. This is the absolute error, which is very good, and this is the deflection in the non-dimensionalized uniscale region. Now moving to here, also the problem is that we get the solution in a certain domain. Now we are interested to get the solution in the larger domain. For the larger domain, how we can train in large space-time domain for multi-similar problem. Here we want to utilize physics-informed neural network-based method, which train stepwise. So we utilize causal pin, and here are some comparison. So basically we perform training stepwise, sorry. So once we train the parent pin model respecting causality, now we want to utilize the trained weight for other multiple similar kind problem. And the multiple similar kind problem, what we consider like different force, some noise in the force, and different initial condition. And this kind of similar kind of problem, we use the trained parameter from the parent model to the other similar kind of problem. So this is all about the transfer learning and causality. This was also my previous work. So now still the challenge arises. Even after the transferring the knowledge, training still required in the transfer domain. So the question is, can we predict outside the trained domain without using any data therein? Which is very crucial for railway dynamics, for long time moving dynamics, moving load dynamics. Now the global challenge, it's not the challenge about the railway, it's a global challenge because data collection is restricted. It is not feasible to collect data everywhere because training domain is limited, and we are interested to generalize and extrapolate. It's necessary. And even deployment where training is challenges such as space exploration, here also we are interested to perform generalization. So here is the training region, and we want to get the results in the annular region. With this, is the case like does the challenge of generalization arises only for physics informed machine learning or pins? Of course not. The challenge is globally relevant for deep learning, regardless of data or physics based, at least for regression based problem. Here I took like sin x function. Here we perform the training. This is the training data. So in the extrapolation region where we didn't provide any training data, it fails. So DNN itself struggled to extrapolate for even simple mathematical function. So now, in what region basically we are interested and what do we mean by extrapolation? In this slide, I would like to discuss like for the beam deflection, predicting beam deflection means we want to train pin. And then predicting beam deflection outside training domain, it means we want to generalize pin solution. For long time dynamics, it means generalizing in the temporal domain. And for Euler-Bernoulli-Timoshenko beam model, as I just show like the several parameters, so we are interested to extrapolate an unseen parametric space. And these parameters, this is an additional independent variable in the training. So basically
Taniya,
we are... Yes.
Can I ask something here?
Yes.
So the way okay, can you hear me? The way you're setting up the problem, it seems to me that you could consider neural operators instead of just pins, because like physics informed neural operators, because you have so many different conditions and you parameterize all these conditions. So would the neural operator be appropriate also here, physics informed neural operator?
Yeah, actually we didn't try this, but I think I can think for this physics informed neural operator. Yes,
right,
of course it's.
Because you can see here you have like parameters, so that could be a distribution. You have
yes.
the one model or another, so that could be also parameterized, and right, with the same equation you can have a parameter in front of this the extra terms. So it seems to me that could be set up also. I just think maybe you can think about it. It just strikes me that the way you set up the problem and all these different conditions, that this would be a pretty good case for and motivation for using neural operators here.
Okay, I will read and try to implement this neural operator for this problem. Thanks. So here, so we are interested in extrapolating in temporal and a parametric domain. With this, like we understand like we want to extrapolate in the temporal and parametric space. With this, I would go to the methodology. Here, I will discuss autoregressive method. So autoregressive, our aim is to not use any data beyond the training domain. So this problem now it reduces to the forecasting quantity based on the present and the past state. For example, stock market prediction, weather prediction, and others. So basically what autoregressive models are appropriate for this, it uses present or past value to predict. So it is not the case like we can just use this one. We can also use for the prediction of X3, we can use X2, also the information from X1. So this is like once future values are obtained, they are used iteratively as a long rollout strategy. This is the idea about the autoregressive. With this, recurrent neural networks, which is well suited for sequential data. Here, for updating the hidden state, we have this transcendental algebraic equation, but there is an issue with exploding and vanishing gradient. Here, for updating the hidden state H2, we need information from the previous cell and this X2 input for updating the hidden state. The issue with the exploding and vanishing gradient for recurrent neural net. Now, what about the ODs for hidden state? If we utilize the ODs for updating the hidden states, it's just similar like recurrent neural network, but the update formula for hidden state is now ODs. Why we are interested to utilize ODs for hidden state? Because it's empirically better performance than vanilla and gated architecture in several AI tasks. And it has bounded gradient, which mitigate exploding and vanishing gradient problem. Now, one of the neural OD method is coupled oscillatory recurrent neural network. Here, the idea of the hidden state is just they just replaced hidden update formula of hidden state with second order ordinary differential equation, which changed into two system of first order ordinary system. And here, Euler scheme, explicit Euler scheme is utilized. Here, first we get the value for Zn, and then we utilize the value of Zn in the hidden update formula. Once we get, and this hidden state formula, the update for the hidden state, it's performed at every sequence. Like for every co-RNN cell, this OD will must be solved. And then we get the update for the hidden state, and finally we'll get the output. So this is the idea about the coupled oscillatory recurrent neural network. The next neural OD method is long expressive memory. This is LEM. Here, the difference with the co-RNN is that here we have two hidden states instead of one hidden state. Two hidden state, it means we have for two hidden state, we have two ordinary differential equation and two update formula. This is the linear component wise multiplication and all these. For updating these two hidden state, we utilize Euler scheme, and we get the update for the hidden state, and this is LEM. And now what the main I would like to present, this is the physics informed machine learning oscillator framework. This oscillator framework we utilize for extrapolation basically. So the first task is to define the problem. That problem, if we are interested in time or a parameter, first we define the problem. Then we train using any physics informed machine learning method. Pins, any pins-based method, causal pin, essay pin, gradient pins, any. Once we train the model, we get the output. Now we need to reshape our reshape the output which we get. And that reshaping must be done slice-wise or stepwise. Here, the output for the time 0, here time 1, time 2, and so on. So once we reshape this, now the task is to train the oscillator, which is the neural OD I just explained, which is co-RNN or LEM or any neural OD method. Like here, we can use like any PIML method. Here, we can use any oscillator, any neural OD based method. Once we train the neural oscillator, we utilize the trained parameter for the next update. But the most important thing is like for the testing, we utilize this last time step output, and then it will done autoregressively for the next. Like for the next output, we utilize the previous one. For the next output, the next output become the input. So this will done autoregressive. This is the physics informed machine learning oscillator framework for extrapolation task. With this, now I would like to move towards the results.
Excuse me. Can I ask a question about the methodology? This is Panos Thinis from Pacific Northwest National Lab. So if I understand correctly, you train the oscillator with data that is provided to you by the, let's say, the physics informed machine learning model, right?
Yes.
For the different time steps. So why do you have to use a physics informed machine learning model if, for example, you can use data from some traditional solver, right? You don't need necessarily the physics informed machine learning model to train the oscillator.
Yes, you are right. We can utilize any neural OD, any method, any favorite PD solver, whichever, finite element, finite difference, any method is fine.
The reason I'm saying this is because the data that the physics informed machine learning model will provide you will come with the error of training the physics informed machine learning model, even in the training domain, right? For time
exactly.
t. So that will then be fed into the training of the oscillator, which then you hope can generalize in times that are further out.
Yes, exactly. You're right.
Than the training time. So is there any guarantee that, this actually will learn will train well? I'm talking about the neural oscillator. I understand that you have good results, but is there any guarantee that going through this approach actually is better than using a traditional solver to provide data to the oscillator network?
In terms of guarantee, of course not, but I can show you one result, which we basically
I'll wait for the
observe.
results. You don't have to show me the results. I'll wait for the results later since you have something planned there.
Yeah, so for on that result, we actually train pins with different errors, and then we see how the as you just mentioned, that how the error is propagating. So indeed it is propagating, but not linearly. It was
Okay.
propagating, but not in the linear. It's not direct proportion, like when the error in the pins, it was like in the range of 10 to the power of -2, but in the oscillator it is not in the same proportion, I mean in the same order of magnitude. It is one order less magnitude in the propagation
Okay.
of error.
All right.
Yes, but
I'll wait for the results. I just wanted to ask if there is any inherent reason why training the neural oscillator with data from pins is better than training with data from a traditional solver.
No, here we can use any method. Not
Okay.
Can I ask follow up on Panos' question, because Panos is right, but the moment you have some data, including historical data from these tracks and so on, how would you bring them in? So the physics in machine learning would make sense in the case where you have some data, not necessarily current data, but even historical data. So then it would make sense. But Panos is right. If you just do, prediction of an idealized case and so on, and you don't use at all data, there's no need to do it. But the moment you have even one data point, I think you may want to consider, or historical data. You can bring historical data through these functional priors and pins.
Okay.
You can go on, Taniya. You can go on. Sorry for the interruption.
No problem. So this is the physics informed machine learning oscillator framework. With this, I am now moving towards results. So for results, we have like 4 different metrics. First is L2 norm, and second is explained variance score. Third is mean absolute error, and maximum error. So there are all the terms, like N is the number of testing points, UI is the reference solution at ith testing data point, U star predicted at ith testing data point, and U bar represents the mean of reference solution. So we, because it's quite difficult to differentiate with the I norm, so these 4 metrics will help to get actual difference between the errors. So here, first test case is Berger's equation. Here we consider the viscosity in 0.01 by pi. We consider the training domain is x lies in -1 to 1, and time is 0.8. And the extrapolation region is 0.8 to 1. And here are the initial and the boundary condition. As we can see in the extrapolation region, RNN is like not good enough to capture the shock. And here is the result for LSTM. Now, here are like GRU, and this is the reference solution. It should be sharp. So for LEM and co-RNN, they both perform better than RNN, LSTM, and GRU for Berger's equation. Now moving toward the second test case, which is on Allen-Kahn equation. Here, RNN is like totally failed in the extrapolation region. And for the LSTM, little better. And here for the GRU, if we observe closely, GRU giving good results, comparative results with co-RNN and LEM. And this is the reference solution. So it's quite, of course, LEM and co-RNN is little better than GRU, but they all are comparative, very close enough, accurate. With this is the third test case which we have used, which is Schrodinger equation. Here the considered domain is -5 to 5 and time is 0 to 2 pi by 5, and the extrapolation region is 2 pi by 5 comma pi by 2. So these are the initial condition. Here RNN LSTM performing very bad for extrapolation region. But here are the GRU results. This is LEM. LEM performed better. And this is reference solution and co-RNN results. And for the final test case is the Euler-Bernoulli beam equation, for which we are interested, which show the deflection results. Here RNN is totally failed, although this is the linear partial differential equation, but this is fourth order equation and it's quite challenging. Here also LSTM totally failed. Only LEM and co-RNN gave better results for the case of Euler-Bernoulli beam equation, and this is the result for GR. So this is the proper comparison for using all four metrics. Here we can see like LEM is the best for all cases, for all metrics also. As I said, like Ln-Khan equation for GRU is quite comparative results with LEM, and the second best in all cases is the second neural OD method, which is co-RN. This is DPM, which was the state of the art before they use some optimization method for extrapolating. And so these are all results for explained variance score maximum area. And now with that, I would like to move towards some additional results. This is the sensitivity analysis. Results, they are the parameter in co-RNN and LEM, which is delta T. So we just changed the delta T and tried to see which is the most sensitive, which is the best value for delta T. And we found that 0.1 was the best. And this is the ablation study for co-RNN. In co-RNN hidden state update, we have two parameters to have a parameter, which is epsilon and gamma. We train our model for 5 different epsilon and gamma, and this is the ablation study. This was the table for which I was saying. The error is propagating, but the error is not propagating like linearly. Here you can see like when the pin has the error like 10 to the power of -3, the overall error of the framework is in the range of 10 to the power of -2. Here, when the error in the pin is 2.6, then the overall framework error is 4.7. So this is all the additional results for the Burgers equation. Now, the second, which I mentioned, like we are interested to extrapolate in the parametric space. So for the parametric space, we consider beta in the range of 0, 40. Here, when we perform the training with 25%, then this was the prediction for beta 40. And when we provide data for 50%, then this is the prediction for beta equals to 40 at final time. And as we can clearly see, when we provide more data, the accuracy is getting better. So this is for here, we provided 80% data, and it's much better than these two previous cases. And similarly for nonlinear heat equation also, we observe this. And here we change alpha in the range of 0, pi. And for the Burgers equation, we change the value of gamma in the range of 0.005, 0.005. And this is the overall results when the beta is 32, 35, 40, and the results for the L2 norm. And now I would like to move towards conclusions. So the conclusion, the contribution and the takeaway from this presentation is generalizing neural PD solver is a long-standing challenge in AI for PD. This work tackles long rollout for time-dependent and parametric PDs. And this is resolution invariant pipeline. PIML model and oscillator process data at different resolution. The contribution are actually beyond pin and extendable to any PIML model, DeepNet, etc., with any other oscillators in the framework. So idea is to leverage classical mathematical models, ODs, infuse in neural architecture to extrapolate PD solution. And our future work is to extending the study to real-world data, generalizing catenary pantograph prediction, and we are interested to predict multi-input, multi-output parametric problem. Thank you so much for your time and giving me opportunity. And I would happy to take any questions.
Thank you so much, Taniya. It was a really interesting talk. You did a lot of work. Do you have any questions from the audience?
Hi, Taniya. This is Kamal from Brown. I have a query on, I think, slide number 9.
Slide number 9. Yes.
So like the mass of the train is much more than the track mass. So is it not like a couple system?
Yes. This is coupled system.
So I was thinking like this is like the mass of the at this mass is also changing with time or no, because it's moving also.
Okay, mass. For this, in this equation, there is no mass.
The density.
Because we,
The density.
Density. I
is
think the density
yes.
is effective density.
Yeah, because we change into non-dimensional, we perform dimensionalized analysis. So while training, it is in the range of 0 to 1, and then we what was your question? Like mass is changing with the
mass
load,
is changing
right?
with time. Because
no, we consider fixed density for our case. Yes, for the real scenario, of course, it must be changing, but for our case, we consider the fixed density.
Okay.
Taniya, Kamal was working on this problem when he was in India. He had real data.
Oh, wow, nice.
For 7 sensors. He still has the data, I think, with his
Yes.
advisor. So that's why I think they have a little more complex models, more realistic models maybe for this. You can talk offline, but I think that's why his question come from.
Oh, thanks. We will discuss.
Hey, Taniya, this is Raj. I just wanted to ask this question on this slide. Did you solve this equation from PIN?
Yes.
There is a bi-Laplacian. In a strong form, did you solve it in the weak form? Because your load is delta function.
Yes, basically for the delta function, we approximate the delta function with the Gaussian distribution. Then we utilize PIN framework. Then we use PIN.
Okay, you may want to look this equation in terms of the weak formulation.
Okay, I will.
Yes.
I will try. Yes.
Raj is right actually, because we both the Timoshenko beam equation and the Euler-Bernoulli, some data worked on it, and she used the variational formulation, and then you can also use delta functions.
Okay. Yes, I will try definitely. Thanks.
So the delta is like at one place, like locally supported, or a distribution along entire beam.
For
like the load. Yeah, for this problem where you approximated with Gaussian.
Yes, but we consider at one location, not moving.
Okay.
Yeah.
And also, if you write it in the weak formulation, one order of the derivative will be less. So your uxxxx will be like third order derivative. So because in weak formulation, you do the integration by parts. So that will help you to reduce the complexity.
Two actually,
also.
Raj, two. You can integrate twice. Yeah, integrate twice.
Yeah.
And then you have a symmetric operator, just like we do in finance.
Yeah, exactly. Yeah.
Okay.
So,
thanks.
and it will reduce the complexity also. So it will be quick actually. So
yeah, I don't know if some data is attending because she's now at Johns Hopkins, but she has done this problem and also put sensors there, find where the sensors are kind of similar type stuff, but without extrapolation. So that part is using.
Yeah. Thank you.
Sure, that's a good talk. Thanks.
Thanks for your question. And
You remember Taniya? You remember Raj, right?
Yes, I remember you also. You gave great talk and great lecture there. It was amazing. I'm still using all the notebooks and the lecture notes which I prepared there.
That's great. You learn a lot.
Yes.
This is Suku from Davis. Can I ask a question now?
Yes, please.
Yeah, so going back to the earlier discussion with Panos and also George. So instead of pin, suppose you had just used the exact solution, for the forward problem. And then especially the the exact solution. So it could be a good verification test for your method to say in the
Yes.
best case scenario, how would your oscillator do, right?
Right.
Yes, exactly.
So
Nice.
that, and also the other related question is that, when you have shocks, for example, in a problem where in future time something is happening, I mean, and you don't use that, and you use data only from 0 to t, and at 5t something is happening. So how is it even possible that your oscillator will do a good job, right? Because it's, it doesn't have that information that something is happening later on. It's like it's similar to doing a boundary value problem with a boundary layer, for example, and you take a smaller domain and then solve a problem, and then the boundary layer is afterwards, right? So it won't see it, right? It doesn't know how the solution must vary later on. So that was just a
Yes.
comment, right? So anyway,
Thanks.
something you can think about.
Yes. Thank you.
Suku, hi. Good to hear from you.
Yeah, likewise.
But that's a good point. If you have downstream, if you have bifurcations, how would you? If this is the dynamical system would bifurcate, how would you? Obviously, cannot. So you need some.
Yeah.
Yes. Thanks.
Yeah, it's nice to hear from you, Suku. I hope you're doing well.
Yeah, good. I just had a fracture yesterday, but so my hand messed up.
Oh, I'm sorry to hear that.
So for 2 months, I can only see videos. I can't write anything.
Oh,
Right.
oh,
Yeah.
I'm sorry.
Yeah,
I'm sorry. I hope you get better soon.
Yeah. Good. Thanks. See you.
Yeah. Regarding about what you just say about the moving forward in time slowly, I think you're kind of taking care of that because if I understood correctly, you're using causality, right? So when you use causality, your loss evolves
Sorry,
in
what?
time. You're using causality, causal pins. You said you were using, right?
Causality. Okay, yes. Yes.
Yeah. So then when you do that, you take care of the time, right? Then when you do the causal pin, you learn the model, learn the problem as you
Yes.
follow the time. Yeah. So I guess that's. I'm fine. Did you try to in your final framework? Are you using the causal pins or not?
For the Schrodinger equation, we trained using causal pen, and for the extrapolating, we used neural OD.
Oh, okay. I see. Great. This was a great talk.
Thank you.
Do we have any other questions from the audience?
I think that's it. Thank you very much, Tanya.
Thank you so much, George. Thank you so much.
Danielle, thanks for. Oh, Matthias may have a question.
No, I just switched on the video to say goodbye. But maybe if you want to have a question, in the first application, I was not sure if you can assume that the solution is periodic with the train.
For the first, can you?
I mean, the application with the beam.
Yes.
Do you assume periodicity or not?
No, we didn't. No.
Okay. Because I know these time series models that you mentioned. I know this from electricity markets, and there you have some they have some standard approach that you first transform the periodic part that is somehow the underlying process. You transform it away by wavelets, and then you make the machine learning only on the deviation of the main process. and then afterwards you put this main signal again back to the solution. And this is much better than taking the whole solution. Okay, then I give you a second question. I think I was a bit surprised that you must know I'm a mathematician, so a techno-mathematician. So I was surprised that you are solving so different types of PDEs. Yeah, so a singular perturbed or convection dominated parabolic PDE, and also a cubic Schrödinger equation. I mean, they are very different, but it seems that you are using the same approach. And I think if you want to achieve further improvements, you must somehow focus on one type of PDEs. So far, it's a very general approach.
Okay.
As for example, if you go for Schrödinger, then usually they are posed on unbounded domains, and they have some conserved quantities. So they have many things that you have to respect, and other PDEs have other special properties that you have to respect. It's not only the residual; it's also the structure of the PDE.
The structure, yeah. Maybe Daniel can answer that. So I think they're trying to show the generality of the method, but I agree with Matthias. When you focused on specific one, then you can bring in the structure, and therefore actually, just like we did in our work with the generic framework, when you bring in the structure, then you can extrapolate much longer, in fact. So these extra properties allow you to extrapolate more safely, let's say.
Right, but I think it's a trade-off between generality and accuracy.
Yeah, of course.
So I think Taniya attempted to show a very general framework, right? That is clearly suboptimal. It could for each particular type of PDEs, it could be improved.
Yeah.
Right.
So, for example, if you have some problem from mechanics, you can think of that you have a Hamiltonian formulation that you are something like this.
Yeah, exactly. That's what. Yeah, exactly.
Right.
So we have a bunch of papers on this, Daniel, on not just Hamiltonian systems, but also dissipative systems. They follow the generic formulation. Jan has published a lot of papers on this, and also Nat Trask has published papers. And some other people in Spain, but it makes sense if you consider the beam and the with the moving masses that come out with changing masses or densities that Kamal talked about to actually impose some structure in the extrapolation.
Right.
Okay, do you have any other question?
I think it's more of a comment. So because are we still recorded?
Yeah, you can stop recording.
Okay, so let me. Okay, thank you so much, everyone. I'm going to stop recording.
I think